Okay. We left off last time with the disk method. And the disk method, you sliced a solid that was revolved around an axis into disks, and you got the volume of a disk that had a width of delta x, and then as you integrate, those delta x's go to 0, and you wound up with the volume. Now we're finally going to get into what I introduced a few slides ago, which was the washer method. And I got to rearrange the slides. But the washer method is when you have a revolved solid that has like a hole of some kind in it that is also a revolved shape. Okay, so like in this case right here, you have a hole in it right here, right? And so the part that's being revolved is this chunk out here. You don't want to include this part here. Let's get this part is not part of our solid. However, that hole in the middle is also a revolved, quote, solid. It's not part of the green. It's empty. It's a revolved empty solid. Did that make any sense? Some student's going to be watching this in 3 years going, what? I'm glad I didn't have him. So the space inside is also enclosed. It would be enclosed inside a revolved. This line, in fact, right here, y equals 3, if it were revolved, would make that cylinder inside. Okay. So this is still a solid of revolution, but cross sections are the shape of washers. So cross sections would look like this. And then you have so this is the cross section right here. Right? And it has a hole in the middle that's not there. So what you have to do is you have to compute the volume of the outside solid and subtract the volume of the empty space in the middle. I got big enough. People are looking out there. Okay. All right. So, is that going to work? All right. First of all, I would recommend getting a graph or some kind of drawing of what's going on here. At least of the region that's being revolved. So find the volume of the solid generated by revolving the region bounded by this parabola and this line. Okay. This parabola and this line. So that parabola, how do you graph a parabola? You can graph a parabola. Shake your head, yes. Please tell me you can graph a parabola. This parabola right here has what? It has a y-intercept. Has a y-intercept of -4. The y-intercept is always the constant term in any polynomial function. So -4 is the intercept. We know it opens up. We know it opens up. Now, don't do this in your paper, but how do we know if it goes this way or does it go that way? It's going to go through that point, -4, right? How do I know which way it goes? Do you know how to get the vertex of a parabola? You should. It's an algebra operation. I'm going to erase all that. There's only one of those is right. So you have here 1 minus 2 minus 4. This is A. This is B. This is C. One way to do this would be to find the x-intercepts. Find the x-intercepts. What would the x-intercepts be? That's where this equals 0. That does not factor conveniently. It does not factor conveniently, right? Another way is the x-coordinate of the vertex is minus b over 2a. And so minus b is positive 2 over 2a is 2. That's 1. And so the y-coordinate of the vertex is the functional value of 1. And that's going to be 1 squared minus 2 times 1 minus 4. All right? And so that is 1 minus 6 is negative 5. So the vertex is 1 minus 5. So this is minus 4 here. Well, 1 minus 5 would be like right here. And so our parabola would be something like okay. So that's an algebraic procedure. It's not calculus. Oh, by the way, you could get it with calculus. How would you get it with calculus? That's a Calc 1 problem. How do you find a minimum in calculus? How do you find a minimum? One, two, three, four, five, six. 6. How do you find a minimum in calculus?
I forgot. Who's 6?
Huh?
Am I 6?
You're 6.
Yeah.
She was about ready to answer anyway because she just assumes it's her number. So this is using algebra. So using calculus, you take a derivative. You want to know where there is a critical number, a critical point, where the slope is 0, right? So you have f of x. Your function is f prime is what? 2x minus 2. You set that equal to 0. That gives you 2x equals 2 or x equal 1. So it tells you at x equal 1, you have a critical number. So you know the slope is flat at x equals 1. Now you also know it opens upward because the leading coefficient is positive. So that should tell you right away it's a minimum. But let's suppose you don't notice that. How do you test whether that's a minimum or maximum? You use either the first derivative test or the second derivative test. And since I'm just in the mood, f double prime of x is 2. That is greater than 0. So that says f is concave up. at x equal 1, which implies that f has a relative minimum at x equal 1. All right, so there's some more calc review. How about this line right here? Y equals x minus 4. Y equals x minus 4. Well, it's going to go, don't write it in your paper, it's going to go like that. It's going to go through minus 4, the slope of 1, right? The question is, where does it intercept? Where does it intersect this? Does it intersect it down here? Or does it go up like that and intersect up there? How do we know? We're going to set x squared minus 2x minus 4 equal to x minus 4. This will tell you the x coordinates at which it intersects. Now, we're expecting one of these to be at 0. We expect x equal to 0 to be one of the places it intersects. We know it intersects there. Where's the other spot? Well, these go. And so I get x squared minus 3x equals 0. X times x minus 3 equals 0. So x equals 0 and x equal 3 are places those two intersect. And so the other coordinate right here, this coordinate right here is going to be x coordinate of 3, a y coordinate of 3 minus 4 minus 1. You got to do all of this just to set something up to apply the shell method, disk method. You have to do all this to do one of these problems. Now, I kind of overdid this over here on finding the vertex, because those are skills I wasn't getting answers on. I wanted to review, right? I wanted to review. So you don't have to quite go into as much detail. If you find the vertex, that will help you in any way you find it. I just don't want Calc 2 students not to know how to find minimum and maximum values. All right. So this is the region right here that gets revolved around the x-axis, this region here. All right, so we're going to do that region there gets revolved around the x-axis. How do you set one of these up? All right. Well, you remember if it were not, well, first of all, convince yourself when that gets revolved around, there's going to be a hole in the middle. There's not going to be anything in the middle. The x-axis will go through the middle of this solid, but it won't touch it. So this part gets revolved, there's going to be a hole in the middle of some kind. It's going to be like almost a cone, right? All right. Well, let's suppose we were revolving the parabola and the line didn't exist. If we were revolving just the parabola, it would be what? The volume. If it were just the parabola, the volume would be pi integral from A to B. It would be R of x squared dx. Don't put the dx on right now, but there would be a dx right there, right? You remember this from last time? Of course you remember it because you worked on them last night, right? You did disk method problems last night, right? If you didn't, you need to get into that habit. Right? I know I'm poking you, but you need to be poked. This is uncrammable. Trust me, I tried, right? 40 years ago. All right. Now, this would give me the solid of the volume of that parabola revolved around the x-axis if there was not the line. I have to subtract out the volume of that empty space that is enclosed by the line. So this right here is, the bottom one is capital R of x. I want you to picture there being another, the line the book calls little r of x. Little r, it's a small r of x. Okay? Small r of x. I'm going to have to subtract off the small r of x that accounts for that space. So here's the difference in this technique with the washer method versus the shell method, or excuse me, disk method. That would be the disk method right there. I'm subtracting off that inside empty space. And so what do I have? I have parenthesis minus little r of x squared dx. So the red accounts for the empty space inside, right? Okay. Question. What's big R of x? It's the parabola.
So if it has a hole in the middle, it's gonna be the same thing.
Yep.
Okay.
That's what we have right here. You have to subtract off that volume in the middle. Yeah. And so we have what? My big one is, it's going to get messy. It's going to get messy. It's going to be x squared minus 2x minus 4 quantity squared. Ew, that's icky. I'm going to have to square a trinomial. I don't want to. All right. Then I'm going to subtract the equation of the line. X minus 4 squared dx. Yeah. Okay. You ready for some algebra? Be very careful and, how should I say, deliberate. Very careful and deliberate. Oh, what are our bounds of integration? This point right here is the point 0 minus 4, right? So I'm going from x equals 0 to 3. Not to 4, to 3. Exactly. So I have 0. Perfect. Now, here's the icky part. I'm going to scooch over some more space here. Pi integral 0 to 3 left parenthesis bracket that squared. How do you square something like that? Well, you know, when you have a binomial times a binomial, you do FOIL. Basically, you do the first term times everything in the second factor, and then the second term times everything in the second factor. Well, here I'm going to do this times everything, x squared times everything, minus 2x times everything, minus 4 times everything. What does that look like? It's a mess. So x squared times everything is going to give me x to the 4th minus 2x cubed minus 4x squared. muchas gracias. Minus 2x times everything. Minus 2x cubed plus 4x squared plus 8x. That's minus 2x times all those terms. Then minus 4 times all those terms. Minus 4x squared plus 8x plus 16. Close bracket. Then I got to square the second thing. The second thing is x squared minus 8x plus 16. Oh, the first thing I spot, I got to do it. I got to do it. Plus 16 minus a plus 16. Gone. All right. What I do is I take powers of x in order, decreasing order of powers of x. 0 to 3, square bracket. X to the fourth. Are there any other x to the fourth? No. So that's an x to the fourth.
That was easy.
X cubes. Minus 2x cubed minus another 2x cubed. By the way, I'm going to underline the things I've already accounted for, okay? So that's a minus 4x cubed. X squared. Oh, we get some canceling. Here's a minus 4x squared. There's a plus 4x squared. Well, I have some more x squareds later, but let's at least do those. Then I have a minus 4x squared, another minus 4x squared, and then a minus x squared in the last term. That's a minus 5x squared. Remember I said methodical. Nobody's going to remember how fast you do this. I have to tell myself that, especially when I'm behind at the end of class. That's why I make a lot of mistakes. Oh, well, we got 6 minutes left. I got 4 more examples I want to do. You guys are saying, Mr. Miller, you could be like a normal teacher and just let us go. Class got across the hall got out 20 minutes ago. And we're at York College where we don't take academics. No, don't go there. All right, so I've accounted now for this and this. Okay. Now my x's. All my x's in Texas. Okay. Minus 8x. Oh, plus, here's a plus 8x. There's a plus 8x. And there's another plus 8x. That is 24x. Close bracket. No constants. Okay, so now I've accounted for that one, and that one. Now everything should be either underlined or crossed out. You got to include everybody here, right? Time to integrate. Time to integrate. And this time I'm going to, I think I'm going to bring it all the way over here. All the way over here. Pi, integrate. X to the 5th over 5, bracket. Minus 4x cubed will be x to the 4th over 4, so that's just a minus x to the 4th. The next one, minus 5x cubed over 3. Plus, now this is going to be an x squared over 2 24 divided by 2 is a 12. X squared, 0 to 3. Now, there's a long way and a short way. I know what you're saying. This has already been the long way, right? But since we are
Easy bottom rolling scum. Easy bottom rolling scum suckers.
I cut it off too soon. You got to have it all right. Since we're that, we're going to do it the shorter way. Okay. What is that? We have to plug a 3 in, then we plug the 0 in. Fortunately, you plug the 0 in, you get all zeros. That's a happy meal, right? So plug the 3 in. You're going to have pi. 3 goes here. 3 goes here into the x to the 5th. Don't figure out what 3 to the 5th is. Just put 3 to the 5th. I'm telling you the scum sucker way, right? So 3 to the 5th over 5. Don't figure out what 3 to the 5th is. 243. Don't figure out what 3 to the 5th is. 3 to the 4th minus 3 to the 4th. Don't figure out what that is. 81. 5 divided by 3. Oh, this one's going to be even a little shorter. Oh, even a little shorter. 5 over 3 times 3 to the 3rd. And then plus 12, 3 squared. And then with the fundamental theorem, you plug in 0, you get 0, so there's nothing to subtract off. So what have we here? Look what we got here. 3 cancels with that. 3 makes it a 2. Okay. Now, here's what scum suckers do. What do all these terms have in common? At least a 3 squared. There's a 3 squared there, 3 squared there. That 3 to the 4th contains a 3 squared. That 3 to the 5th contains a 3 squared. So don't figure out what all those numbers are. Pull a 3 squared, which is, of course, a 9. Pull a 3 squared up front and make those numbers smaller. Capiche? My 95-pound Italian mother-in-law used to say. Right? All right, so we're going to do pi times a 3 squared up front. So when I do a 3 squared up front, I am left with, off of this first term, I'm left with 3 cubed divided by 5. Minus 3 squared minus 5/3 plus 12. Oh, did I say no? There's a typo there. That 5/3 went away. That's a 5. And these two combine, they give you a 7. Okay. Now, there's one other way you could have done this. Another way somebody might say, see that 12? That 12 is a 3 times 4. So you could have made this a 3 cubed and brought another 3 up front. But don't worry about it. Now we need to have, we're going to have 3 squared pi up front, brackets, common denominator time. What is my common denominator? My common denominator is 5. Right? So 5. And now's a good time to convert some 3's. 3 cubed is 27. 3 squared, this is going to need a 5 on the top, 5 on the bottom. So that's a 9 right there, basically, right? That's a 9. So 9 is 45 fifths. So minus 45. Seven is 35 fifths. So all that across the top equals, well, that's a 9 pi. And then inside those brackets, 35 minus 45 is minus 10. 27 minus 10 is 17. Okay. All right. So this all equals, what is 9 times 17? Here's how I do that. 10 times 17 is 170. So 9 times 17 is 170 minus 17, or 153. Pi divided by 5. And that is correct. All right. Oh dear, what are some takeaways here? Let me ask you, what do you think are keys to solving that problem? What do you think are keys to solving that problem?
Know what your R's are?
Yeah, oh, that is certainly key. These R's, the inside and outside function, absolutely a key. Absolutely a key. All right. I tell you what, since he started, what do you think a key is in solving this problem? Anything? What was a key step? Anything. It doesn't have to be the next most important. Just whatever. What struck you as even important?
We gotta know our vertex so we can see where plug-in numbers are gonna be.
I think you need the vertex. Not knowing where the vertex was here or over here, that could mess you up. So know how to get the vertex of a problem. Another key would be what to do with your R's. Know what your R's are. In other words, know the inside radius and the outside radius. You square them, then subtract them. Don't subtract them, then square them. I've made that mistake. You square them first and then subtract them. It would be so much nicer if you could subtract them first, then square them. There'd be a lot less algebra. That's probably why I did it that way. It looked easier, right? But you see, we bottom dwellers don't like doing things over. We're so lazy, we don't like doing it over. So this setup here it's really the new thing with this problem. That is really the new teaching in this whole problem. That is how you deal with the hole in the middle. That is the quote-unquote washer method, right? So this is the washer. And all it is an adapted disk method. Okay. Right. Cassie, have you thought of a takeaway? What is that? There's more important things. You thought of one? Be very methodical in your algebra. When there's a lot of algebra, very, very careful. There's a million places to mess up. Right? Whenever you see one number is going to be raised to a bunch of different powers, don't expand that number. You imagine how clumsy this would be if right here we would have put x to the fifth, 243 over 5 minus 81 minus 5/3 times 27. That's x cubed, right? For the 3. Plus 12 times 9. Is that 108? Could you imagine if I if I didn't factor the 3 out, 3 squared? Those numbers would be huge. Actually, these right here. Those numbers would be huge. Right? And you're already dealing with adding fractions. Nobody likes fractions. We all make more mistakes with fractions. So when you have something you see going in, a bunch of different, that 3 is going in all these different places for x. Leave them non-expanded. Don't expand them. Because you're probably going to be able to factor off something like that 9, that 3 squared. And that makes these in here, these are already big enough, right? Okay, 27, 45, 35. A lot easier, though, than those numbers we had before. If we would have kept the 3 squared inside. All right? And then you, 9 times pi, that was on the outside. All that in the brackets boiled down to 17/5. 9 times 17, multiplied however you want. I showed you how I think of that. 9 times anything, I do 10 times anything, and then subtract 1 of the thing. That's how I do 9 times anything. That gives you 153 pi over 5. Right? All right, what's your method? Whoa. Okay. Yeah, something's wrong here. Oh, here we go. Okay. Some of that can probably go on that next slide. Yeah, I definitely will. Right. Yeah, we'll put some of this there. We'll put. All of that. Paste it there. Ooh. All right. And we'll keep that dude down here. Oh, by the way, on your calculator, that's a good way to check your work, right? 1, -5 is the minimum there, right? We got that by hand, but you can check on your calculator. Use your graphing calculator as a learning tool. Okay. Now. Find the volume of the solid generated by revolving the region bounded by these two things. Revolved about the line y equals 4. What's that about? It's not revolved around an axis.
It's like up first.
Yeah, it's up. Yeah, exactly. Exactly. So this is, we're not going to spend as much time graphing this buzzard. But this guy right here, right? That's going to be actually, I'm going to move this guy over some. You know what I'm going to do too? We've written a lot on the screen, so I'm going to, instead of waiting for it to crash, I'm going to get out of it. Back into it. Right here. I'm actually going to go over here and do something a little bit different. I'm going to write my axes like this, because this is going to have zeros at 0 and 2. Okay, so this goes like this. Another way of finding the x-coordinate of the vertex. You don't have to find the vertex here, I don't think. It might help you, though. Is the x-coordinate of the vertex is always going to be exactly between the zeros. So if a parabola hits the x-axis in 2 spots, exactly in between that, the average of the two roots is going to be the x-coordinate of the vertex. And so this is going to be 1, and plug in 1. 1 minus 1, 1. 1 minus 1. Okay. All right? Okay. Now we have a line y equals x. And so that's going to be right? Okay. And so this is our region here. This part here is what's getting rotated. And it's getting rotated about the line y equals 4. So if we revolve that region around the line y equals 4, we have what? Another revolved solid, except it's not around an axis. How do we adjust? How do we adjust for it not being around an axis? Well, a couple of different ways. One thing we could do is we could move this whole thing down forward. So this region revolved around the line y equals 4. That would have the same volume if I moved it all down 4 as this region moved down 4 wrapped around the x-axis. That's one way to do it. And you know what? Even doing it the way we're going to do it, you're going to see that's kind of, it's going to be kind of the same. Okay. So what were the keys? Remember I asked you a second ago, what were the keys to the last problem? His first one was, what are your r's? Little r, x, big R of x. Your little r of x is the inner, it's the inner, the closest, the function closest to your axis of rotation. So this one here, from here, from here to there, that's the inner one, right? What's that distance? What is that distance? Well, this is the line.
The radius.
Yeah, but what exactly? Yeah, it's the radius, but what is it? Down here, y equals x. Right? Up here, y equals 4. Correct? Everyone got that? So that makes this thing in the middle 4 minus x. Yeah. 4 minus x. What's, oh, that's little r. That's a key. Cassidy, you okay on that? See that? All right. What's the big R? It is from there and there. The top one, y equals 4. The bottom one is
X squared minus 2x.
exactly. Well, y equals x squared minus 2x. All right. So what's that distance? Oh, by the way, you could also view this 4 minus x as x minus 4. You can do it that way too, because your radius would be your, this would be your inner minus that, but you're going to get the same, you get the same thing. I don't want to confuse you with that, but right here, that distance is what? That is 4 minus x squared minus 2x. And that equals your big R of x. Okay. So to highlight the important parts, that is little r of x. That is big R of x. Okay. All right. Okay. Everyone, all right. So now our volume.
How do you find the green line, the
This
line?
or this?
Yes.
That was y equals x.
Okay.
And so our formula, go back over to our last slide, actually. 2 slides ago. This was the horseshoe, remember? All right. I know you can't copy it like that, but I hope it provides a little bit of clarity. So V is going to be pi, integral from what to what? Ooh, that's interesting. What is this point right here? What is this point right here? We know we have 0 on the bottom. What's that point over there? Well, it's not going to be 2. It's going to be further than 2. We have to do the same thing we did earlier. We have to set these equal. Y equals that. if y equals x squared minus 2x, y equals x squared minus 2x, and y equals x, then x squared minus 2x equals x. X squared minus 3x equals 0, and x is x minus 3 equals 0. So we have x equals 0, which we already knew it intersected there, and we have x equal 3. So by coincidence, my upper bound, again in this problem, is a 3. Left parenthesis. Okay. Left parenthesis. The outer R of x is this line right here. By the way, that's going to be, what is it going to be? Minus x squared plus 2x plus 4, right? But so that's going to be minus x squared plus 2x plus 4 squared minus little r of x, 4 minus x squared dx. Right? So this is going to be pi integral 0 to 3 left parenthesis. How do you square something like that? Everything by everything. So x squared minus x squared times everything is going to give you a positive x to the 4th minus 2x cubed minus 4x squared. That's minus x squared times everything. 2x times everything is a minus 2x cubed. I'm going to run out of space. Minus 2x cubed plus 4x squared plus 8x. Little barrier there. Then I have 4 times everything minus 4x squared plus 8x plus 16 square bracket there minus this squared. 16 minus 8x plus x squared. Another square bracket, parenthesis, dx. Once again, we got some stuff that cancels. 16, that's a minus 16, that's a plus 16. There's a minus 8x, there's a plus 8x. All right? Right? What is that going to give us? Same thing we did before. We have to integrate now. All right, let's combine terms. I'm sorry. Pi, 0 to 3, square bracket, an x to the 4th. There's no more x to the 4th. So underline that one. X cubed minus 2x cubed minus 2 more x cubed is minus 4x cubed. So we've taken care of that one and that one. Minus 4x squared, you have a plus 4x squared, and then another minus 4x squared. Here's a minus 4x squared, minus another 4x squared is minus 5x squared.
Why did you cancel the 8x's? Because you didn't do that in the last problem.
Maybe I should have. But the reason why I did is you had a positive there and a negative there. You know why I didn't in the last problem? Is
Because you distribute the negative.
well, I had
the last one.
well, I probably did positive 8 minus 8. Let's go back and see what I did. Good question.
Because that negative and negative 4 goes into a positive.
So I did positive 8x. No, positive 8x, oh, minus a minus. Wait a minute, you know what? Maybe we don't. Hold on. Maybe you're right. Let me see. We screw up here. That is a positive. You're right. Thank you, Cassidy. All right. Yes, thank you. So I have again a 24x. And no constants. So I've dealt with that one, and that one. I did that one. I did that one. This is a big coincidence. Does that look familiar? That is the same as the exact same integral as that. So believe it or not, this comes out to 153 pi over 5. Is that a bottom dweller's dream or not, right? And so that is, once again, that's just a coincidence. That is a big coincidence. Got a headache yet? Yeah. The difference here was this situation basically is exactly the last situation moved up 4. Now, go back to the last situation, the last problem we did. This one here. Remember that my axes are these black lines here. If I were to move each of these up 4, what would I have? If I were to move this one up 4, I would have x squared minus 2x. X squared minus 2x. If I would move that one up 4, I'd have y equals x. That's exactly the next problem. So it makes sense that it would be the same volume, right? So if I go back to the last problem and I move each of those functions up 4 units, those constants go away. Now, what I intended to show you in this problem is how to set up something that's not rotated about an axis. Now, why did I use this method here to begin with, or the washer method? It still is a washer because it's rotated not around the x-axis, but it's rotated around y equals 4, which is parallel to the x-axis. And so I can use the same method, right? I can use exactly the same method, all right? Here is a kinder and gentler one for you to do tonight, all right? For you to do tonight. Okay. Related to the disk method. Related to the disk method.
Can you go back real quick?
Yeah.
Please. I know.
Here we took cross sections that were circular. You got disks or washers, but the cross sections were circular. How about if the cross sections are not circular, but you know the shape. Now, since these were circular, we did pi r squared. But if you know the shape, maybe you can come up with the area of a disc or a slice. It won't be round necessarily. All right? It won't be round necessarily. All right. So let's look at that possibility. Oh, you still? Are you
Yeah,
done?
that's fine.
Okay.
Thank you.
Look at this guy. What if the cross sections of a solid are not round, but there's some shape you know the area of? Well, we can integrate that area from A to B just the same. Instead of pi r squared, you got whatever that area is from A to B. All right. And so all you do is you integrate volume, integral A to B, and you integrate the area. Now, let's look down at this solid right here. All right. The solid right here, suppose, you see this shape right here, this kind of gold shape. Suppose you knew the area of that. Suppose it had an area A of x. And the area depended on x. So as that goes through that solid, you plug in whatever the x coordinate is, it will give you the area of a slice. Similar, how about if you had the area this way? And this were A of x. That would actually be A of y. And then it's going through the solid with y varying instead of x. Turns out you can just integrate those a's, the A of x or A of y, and that will give you the volume. I've got time for one maybe of these. Now, you're going to have to be hang with me here. A cylinder of radius 1 is cut by two planes. The first plane is perpendicular to the x-axis of the cylinder. The other one is at a 45-degree angle to the x-axis of the cylinder and intersects the first plane along a diameter of the circle formed by the cylinder. It ain't that bad. Watch. Let's do a cylinder. That's just there. Okay. And all right. Now that's a cylinder of radius 1. So this radius up here is 1. Uno. Now we're going to have a axis go down the middle. Let's make this axis go down the middle. And then this radius here, from here to here, is 1. Now, if you read the question carefully, you have two planes that cut through that cylinder. One cuts through at an angle perpendicular to that black drawn axis. So I'm going to have a plane like that. It's going to make a trace. The cylinder is going to make a trace in that plane that's a circle. So it's going to be okay. Like that, right? Still hanging with me? Now, I want you to imagine a diameter of that circle. A diameter would go like this. Say from there to there. That's a diameter. And the main axis hits that diameter in the middle, right there. So that red is a diameter of that circle. We have another plane that intersects at a 45-degree angle to this plane, and it goes through that diameter. Now, this is going to be the hard one to draw. It's going to be, and what color should I make this? I'm going to make it green as well. So it's going to be that. And that plane,
What is that one on top? The red one?
this,
The one on the.
well, that,
Yeah.
oh, that's just the radius being 1. And so that is going to cut this plane at a 45-degree angle. So right here is 45 degrees. And how is that angled plane going to cut the cylinder? It's going to cut the cylinder like this. It's going to make a wedge. Let me do it better. It's going to make a wedge. I have it drawn better on my paper. Actually, I'm going to do it this way. And it's going to make a wedge like there, there. And so you have there's no other way to say it, a circular wedge, right? You have a circular wedge. And so if I were to look down from the top, I'm going to have the blue circle, radius 1. And then I'm going to have, from the top, this red line is this red line. And from the top, it goes like this. That's what you're going to see from the top of the wedge, right? And maybe from another side, it might look like this. Here, I thought we had enough time to do this.
Oh, my drawing is
It's going to go like, I know, it's sad.
Sad.
Like that, like a wedge. All right. And this line right here is the diameter. That line there is this line here, the diameter. Okay. Yeah, it's pretty sad.
So this wedge is a piece that's being taken from the cylinder?
It's not being taken, actually. I removed it so you can see its shape. We're trying to figure out the volume of it in the cylinder. And so this blue circle is the cylinder from the top. So if you look at a cylinder from the top, you see a circle. And then that diameter is this diameter. It would be this diameter. This is looking from a different angle, right? And now there's a top surface. So if you were to look at it, oh, this is another one. If you were to look at it from this way, you would see a triangle. So if you were to look from this angle here, from from that way, you would see a triangle. Cross sections here, this is very important. A cross section of this would be a triangle. That would be a cross section. And there is a right angle. I don't like my triangle. That would be my triangle. Now we have to figure out the area of that triangle in terms of x. So we're going to treat this is the x-axis here. And so here's the base of that triangle. That is that.
Don't give us just on the examples.
You're likely to have one similar. Okay. There's all kinds of ways. The point is you have a cross section. And now you got to ask yourself, okay, what is the area of this triangle? Yeah. Well, you know that triangle looks like this. That thick base is here. Oh, one thing I didn't say over here, this angle here between here and here is 45 degrees. So that means this angle is 45 degrees. So I have a triangle . What's the area of that? Well, if this is 45, then whatever this distance is,
That's one.
not necessarily, because over here it would be no. It would be the big at its biggest point. It would be 1. At its biggest point would be 1, but this right here would be whatever the height of the circle is. So this circle is x squared plus y squared equal 1. So the height, this right here, is y is the square root of 1 minus x squared. And so that makes this the square root of 1 minus x squared. And that makes this the square root of 1 minus x squared. And here's the key. Area is 1/2 base times height. That's 1/2 the base square root 1 minus x squared. The height is square root 1 minus x squared. And so that makes it the a of x is 1/2 1 minus x squared, which is amazingly simple for such a complex situation, right? And the last thing I'll do before I let you go, we're not going to finish it. What is our volume then? Our volume is integral a to b, a of x dx. That's going to be 1/2 the integral from -1 to 1, 1 minus x squared dx. Oh, shucks. That equals 4 pi over 3. Sorry, 4/3. Very simple integral in the middle, because that's going to be 1/2 x minus x cubed over 3 from -1 to 1. And comes out to 4/3. All right. We went a couple minutes over. I'm sorry. What will happen is next time I will go through this problem again. So we finished a little bit hurried. All right. But the point is that you found the area of a slice and you integrated that area function. See you next time.
Have a nice day.
Ah, you too.
Thank you.